All right, in this video, we're going to go over integration by parts for those of you who missed it or you need a refresher. We didn't quite finish it in class, so here we go. Integration of parts is going to use this formula, which is derived by using the product rule. So if we, product rule for differentiation, if we take two functions, u times v, and we take the derivative of that product, then we know that we're going to have the first, which is u, times dv, plus the second, which is v, times du. And then if we integrate both sides, we integrate the left side, we integrate the right side, we're going to integrate, since this is a sum, we just can integrate both of the terms here. So an integral or antiderivative of a derivative is just going to return back the uv, and then over here we're going to have the antiderivative of u dv plus the antiderivative of v du, and then you should be able to see simply that if we solve this for the integral of u dv, we can subtract this from the other side and we end up with this formula. So this formula is going to be another technique for integration, very helpful to be able to solve integrals that we normally can't solve, even simple ones like the integral of natural log of x dx. Seems like a very simple one, but cannot be solved unless you use integration by parts. And so for this, we're basically going to break up the integral into a u and a dv. I'm going to show this two different ways, the traditional way and then a new way with tables and called the DI method. So in the traditional way, we have to figure out what our u is and what our dv is. U, we want something to be easily differentiated, and dv, we want something to be easily integrated. So here's our first example, and to start off, I tell you what u and dv are, but normally you wouldn't be told what the u and the dv are. You have to figure out what they are. And after doing some of these, you should be able to see some patterns and some hints of like which part is which. So here we're going to let, you can see we are trying to take this integral, and we're going to let u be just the x part, and our dv is going to be this e to negative 4x dx. So this is the traditional way. We say u is equal to x, and then we have dv is equal to e to the negative 4x dx. And the u we want to differentiate. So whatever goes on this side, we're going to differentiate. I'll put a d there for differentiate. So the derivative of just x is going to be 1 dx. And over here, we want to integrate. So I'll put an I over in this column. And that'll lead us into the other method of setting these up. So if we take the antiderivative of dv, we get v. And then the antiderivative of e to the negative 4x, this is just e to the u, which is going to be e to the u. And then we have to, if u is negative 4x, then that means that du would be negative 4 dx. And so we have to end up dividing here as well. So we divide by negative 4. Now we can use this formula, which says that that this integral that we had originally is going to be uv minus the integral of v du. So the original one that we had set up here with u and dv, now we write as uv minus antiderivative of v du. So what is u? U is x. We multiply that. V is this part here after we integrate, which is e to negative 4x over negative 4, minus, now we take this integral, which should be something easier. Now we have e to negative 4x over negative 4 dx. And this part we don't do anything with. We just get x e to negative 4x over negative 4. This part we have to take the antiderivative. We can pull out the negative 1/4. And this is again e to the u. So that's going to be e to the u. We're going to divide it again by another negative 4. So we're divided by another negative 4. There's already a negative 4 down there. Negative 4 times negative 4. Hopefully you can see that's going to be 16. And then don't forget the plus c. And there is our answer. So again, this is the traditional way to do it. And now we're going to start using a new method called the DI method. And if you saw the video that I posted from BlackPenRedPen, he goes through 3 examples. So we're going to be using that for number 3. So here we have the integral of x, natural log of 2x dx, and again it's telling us what u is and what dv is. Again, the new method here is that we're going to set up 2 columns, a d column and an I column. And by doing this, we don't have to keep track of, the u's and the dx's and the du's and the dv's. This column we're just going to differentiate. This column we're just going to integrate. And then I'll show you how we get our answer from it. So the d is going to be the thing that's going to be differentiated. So it's normally going to be the u in the traditional way. And the I column, you're going to put in your dv in the traditional method. So here, we're going to differentiate natural log of 2x. And we're going to integrate x. And I'm just going to write x here instead of x dx, so that we just keep track of the thing to differentiate and the thing to integrate. The other thing to remember when setting up this method is that we're going to have several rows possibly going down here where we just differentiate all the way down, integrate this one all the way down, but the signs are going to alternate. So it first starts out with a plus, then it's going to be a minus, then a plus, then minus, and so on. So we start with natural log of 2x, and if we differentiate that, we basically any time that there is a log or a natural log, this is always going to be pretty much always in the u column. Maybe not always, but it's a good rule because for one thing, we can't integrate log of x or natural log of x without using integration of parts. So if you see this function, it's going to be used in the d column most likely. So now we're going to take the derivative here. The derivative of natural log is 1 over u, in this case 1 over 2x, times, don't forget the chain rule, times the derivative of the inside, which is just 2. And if we simplify that, that's just going to come out to 1x. And normally we would differentiate this again. So this is 1 over x, which is the same as x to negative 1. So the derivative of that would be negative x to the negative 2. And you can see that, you would just keep differentiating normally. But here we're going to start working with this column. And when we integrate this, we're going to have x squared over 2. If we integrate again, we would have x cubed over 6. And we would, continue integrating this. Now, when do we stop? The thing is that we either stop when this becomes a 0 anytime, or there's a couple other reasons, or we get something that repeats from the original. Well, here it doesn't. If we get a row that repeats from the original, or if we get something that when we multiply it, we can integrate. So if we look back up here, we should have stopped here because when we multiply 1 over x times x squared over 2, we're going to be left with x over 2. So this is the place where we're going to stop for this one. So when we're doing the DI method, there are 3 places to stop. Either you stop when you get a 0, you stop when a row can be integrated, or you stop when a row is repeated from what you have read or seen originally. So we actually don't need this row here. Now, when we get our answer, we're going to take this diagonal. This is going to be basically the u times v, and that's going to be natural log of 2x. Now I'm writing my answer. And that's going to get multiplied by x squared, which we're going to put that out in front, over 2. So there's the uv part, u times v. And then this represents the integral that we still need to do. So now we're going to subtract off the integral, multiply this out. X squared over x is just x over 2 dx. And continue to solve this. So now we can take this antiderivative, and this is x squared, natural log of 2x over 2, and this is going to get bumped up a power, so it's going to become x squared divided by 2. It's already divided by 2, so that 2 times 2 gives us 4, and don't forget the plus c, and we've got our answer. Number 5, here we've got log base 5 of x dx. So again, anytime you see a log or a log of a different base or a natural log, that's typically going to be your u part. And again, we could do this the traditional way of setting up u and dv and writing out that way with the formula. Remember, this is the formula that the integral of u dv equals uv minus the integral of v du. So this is the traditional way to set it up, but we're going to be using the table method, and the table method requires us to write a d column and an I column. This is called the tabular method, or sometimes the di method. The d is going to represent the thing to differentiate, which is going to be our u. The I is going to be the thing that we're going to integrate, which is going to be our dv. And again, when we're setting this up, we're going to make our rows here, alternate the signs, plus, minus, and so on. We're going to take and write our u down here, the thing to differentiate, which we're told here is going to be log base 5 of x. And dv is equal to dx. Well, that means it's a 1 dx. So if there doesn't seem to be anything left over, that's going to be a 1. That's what we're going to integrate. When we're setting up the table method, I'm not writing the dv here. I don't need to keep track of that. And now we go to next row. Differentiate. You might have to look this up. What is the derivative of a log with a different base? Well, it's going to be 1 over x, but then you have to multiply it by natural log, or you have to divide it by natural log of whatever the base is. In this case, natural log of 5. Take the antiderivative of this. That is going to be x. And we have to decide when to stop. So if we keep taking the derivative here, this is never going to get to 0. If we take the integration here, this is never going to get to 0. So we check if a row can be integrated, then we stop at that place. So if we take this and we multiply this out, we would just have 1 over natural log of 5. And that's going to be something that we can integrate. So we're done. We're not going to write any more rows here. So the first part of it is going to be u times v, which is going to be, we're going to put the x out in front. So that's going to be x log base 5 of x. And then this part, we still have to take the integral. Notice the sign here. It says minus, and then take the product. This is going to be an integral if we're taking a row here. And then the x's would cancel out, and it would just be 1 over natural log of 5 dx. This is just a constant. So when we integrate that, integrate any constant, is just going to be the constant times x. So we have x, log base 5 of x, minus x over natural log of 5 plus c. And there is our final answer. Number 7, here we have x cosine of 2x. And we're going to do this with the table method, di method. di, differentiation by parts. D, again, is going to be the u, the thing to be integrated. I is the thing to integrate. This is the thing to differentiate. This is the thing to integrate. This is going to be our dv. What is our u? Our u here is going to be x. Now, normally, how would you decide? Well, because typically we want something that's easy to differentiate here. We want this to be something that's easy to integrate. X and cosine are both easy to differentiate, and they're both easy to integrate. But we see that if we integrate x, eventually it's going to get down to a place where it's 0. And that's great. So cosine, if we integrate that, is just going to flip-flop between cosine and sine. So in that case, we want to put the thing that's eventually going to get to 0, probably in this column. So if we write x here, and cosine of 2x over here, that's the way we're going to set this up. Remember, our rows are going to go plus, minus, and so on. And we just differentiate. And when do we stop? Well, we're going to stop when, if it's going to keep going, we're going to stop whenever we have a row that multiplies to something we can integrate, or if we get a 0 here in this column. So if we take the derivative once, we get 1. If we take the derivative again, we get 0. And we're going to keep getting zeros all the way down. So we can stop once you get a 0. This one, we got cosine of 2x. Integrate. Well, the antiderivative of cosine is going to be sine of u divided by u or du, which is going to be sine of 2 down here. And if we integrate this again, it's going to be negative cosine of 2x divided by 4. Now in this case, since we have a 0 here, we can just get our answer by multiplying along the diagonal. So this is going to be the first term, x times sine of 2x. So we got x sine of 2x over 2. And then this is going to be our second term. But we've got to keep track of the signs. So we've got negative 1 times this negative is going to give us a positive cosine of 2x over 4 plus c. In this case, we don't have to take the integral like we did in the previous one because we already did. So this is just already did the work for us. We already did the integration up at this point, remember? So now we can just get our answer by multiplying the diagonals. Multiply the diagonals. Here's the first term. Here's the second term. And if we keep going, this one would be 0. So that's why we know we can stop, because we're going to have 0 times whatever this is. We don't have any more terms. So here is our answer. Okay, starting with number 9. Now I don't tell you explicitly what u and dv are. You're going to have to find them. So we're going to do this by integration by parts. Keep in mind the main idea for integration by parts is to break up an integral into things, something that's easy to differentiate and something that's easy to integrate. And we're using this property that the integral of u dv is going to be uv minus the integral of v du. Now, the reason why we're doing this table method, if it hasn't become clear, is because sometimes this integral you have to do by integration by parts again. And then you're going to have another one, and then another one. So this sometimes ends up to be a quite long chain where this integral can be integrated again by integration of parts, which is going to give you another integral, which has to do integration by parts, and so on. So sometimes you can end up with a pretty long chain, and this DI method is going to help to resolve that a lot easier. So now let's look at number 9. So we're going to write out our columns, D, I, put the signs, plus, minus, plus, minus. The rows here, they might continue for a long time, depending on how many steps we need to do integration by parts. The D we want to be our U. That we want to be something that's easy to differentiate. Our I we want to be our dV. That we want something to be easy to integrate. And here we looks like we got two parts already staring at us. We got an x and we got a 2 to the x. Okay, those seem to be obvious. Although sometimes the whole thing goes here, or sometimes, so sometimes the whole thing might go into the D part. But in this case, we've got our x and 2 to the x. It looks like both of these are easy to differentiate. Both are easy to integrate. If we differentiate one of them, will we ever end up with a 0? Well, if you put 2x into 2 to the x here, you're just going to get an exponential, an exponential, an exponential all the way down. So a better choice for our D is going to be the x. Because if you take the derivative, you're going to get 1. And if you take the derivative again, you're going to get 0, just like in the last example. So whenever you get to 0, you know that you're done. And then you can go to this side, and you can start to integrate. So we have 2 to the x. Again, I don't have to write the dx here, it's kind of implied, but we're going to integrate, and that's going to be 2 to the x divided by natural log of 2. And if we integrate that again, that's going to be 2 to the x divided by natural log of 2, which we already have a natural log of 2, so it's going to be natural log of 2 squared. And since we got a 0 here, we don't have to continue on. Since we have a 0, we can just take the parts that we get from the diagonals here. And those are going to get our two terms. So the first term is a positive x times 2 over x, natural log of 2. So we got x times 2 to the x over natural log of 2. And then here we got a negative 1 times this, which is going to be negative 2 to the x over natural log of 2 squared. And then always don't forget the plus c, because these are indefinite integrals. And there we go, we've got our answer. Number 11, x sine of 3x dx. So again, I don't tell you what u and dv or u and dv are. I don't tell you what to differentiate and what to integrate, but hopefully you can see at this point which one is going to be easier to differentiate. Which one is easy to integrate. So they're both easy to differentiate, both easy to integrate. But again, if there's something that you can differentiate that will eventually get to a 0, that's the one that's typically going to go in the D column. So set up your signs plus, minus, so on. Which part is going to go here? Well, probably x. Which part then has to go here? Sine of 3x. Because if I take x and I differentiate it, I'm going to get a 1. Differentiate again, I'm going to get a 0. Once I get a 0, I can stop. Remember, you can stop under 3 cases. If you get a 0 here, or if you don't get a 0 here, then you get a row that's easy to integrate, or you get a row that's repeated. So we're going to stop here because we got a 0. Integrate sine of 3x. Well, the integral is going to be cosine. It's going to be negative cosine of 3x divided by 3. And you can check. Whenever you're having difficulties integrating, just take the derivative and see if you get this. The derivative of negative cosine would be sine. And then the inside would stay the same. And remember, we would have to multiply by the derivative of the inside. And so, yeah, we do get sine of 3x. And we're going to integrate this again. So now it's going to be negative sine of 3x divided by another 3. So 3 times 3 is going to be divided by 9 here. Since we got a 0 here, and we already did the integration, our answer is just going to be along the diagonals here. So our first term is going to be positive x times this guy, which is going to come out to a negative x cosine of 3x over 3. Here we have a negative 1 times a negative times a negative, makes that a positive. Sine of 3x over 9. Here we're going to get 0. 0 times anything is just 0, so we don't have any more terms, but we do have to have the plus c, and we've got our answer. Okay, for number 13, this one involves a natural log of x and involves a square root of x, which is on the bottom here. In order to set up this a little bit easier, maybe we want to rewrite this. So this square root of x on the bottom, we can write as x to the negative 1/2. And then we've got natural log of x dx. So this might make it a little bit easier to do the derivatives and integrals. Now we're going to pick our D column and we're going to pick our I column. And the thing is, if it has natural log of x, can we take the integral, antiderivative of natural log of x? No, you can't. So remember, if you have a natural log of x in your problem, it probably has to go, most likely, in the D column, because to take the integral of natural log of x, you have to use integration by parts itself. So ln x is going to go here. Let's put in our signs right away. So it's going to go plus, minus, so on. And then this is going to be x to the negative 1/2. If we take the derivative here, we're going to have 1 over x. If we take the derivative again, we're going to have, that's the same as x to negative 1. That's going to be negative x to negative 2. And you can see here, you're not going to end up with a 0 in the column. So once you realize that you're never going to have a 0 here, you probably should go to the other column and start integrating so that we can see if a column is going to either repeat or if we're going to get something that we can integrate. So we're going to take the antiderivative or integral of x to negative 1/2. It's got to get bumped up by 1. So that's going to become x to the 1/2. And then it's going to get divided by that power. Divided by 1/2 is the same as multiplying by 2. And now when you multiply these out, you're just going to have a polynomial, something to a power. So at that point, we're going to be able to stop. So we want to stop here and not go any further. We are going to have to take the integral of this guy. So when we write out our answer, this is going to be the first term of our answer, which is 2x to the 1/2, or you could write the square root of x if you want to, natural log of x minus the integral. This is going to go in the integral, and this is a negative, what does that come out to? Negative 2x and this is 1/2, and this is -1. 1/2 minus 1 is going to be -1/2. So we're going to have to integrate this guy to x to -1/2 dx. This part is going to stay the same, 2x to the 1/2 natural log of x. And now take the antiderivative of this. It's got to get bumped up to a power, so it's going to be x, add 1 to that, it's going to go up to 1/2. And then we're dividing by 1/2. So dividing by 1/2 is the same as multiplying by 2. 2 times 2 is going to be 4, and it's got this minus sign out in front. So we're going to have -4x to the 1/2. And don't forget the plus c. And that should be what our final answer looks like. Again, you could write these guys in square roots as well. 15. The integral of square root of x, natural log of 4x. Have to do this by integration by parts. So typically when you have, two different functions here that are multiplied together, and you don't have a formula for it, you probably have to do integration by parts. So we don't have a natural formula for this, and there is no chain rule or product rule for integrals. This is the product rule for integrals. It's integration by parts. So we have to figure out what our d is and what our I is. And again, we're going to alternate signs. What's going to go in the d column? Well, since it involves natural log of 4x, that's going to have to go here. And the I is going to be x to the 1/2. So it's easier if we can write out radicals and things like that with powers, so we can use the power rule. Take the integral of this. It's going to be 1 over 4x, but times 4, so that's the same as 1 over x. If you take the integral again, well, it's going to be, that's x to -1, so it's going to be -x to the -2. And again, you can see that it's never going to stop, so we're going to have to start integrating this guy. This is x to the 1/2, so add 1 to it. It's going to go up to x to the 3/2. Divided by 3/2 is the same as multiplying by 2/3. And now when you multiply this row, you're going to get something that we can integrate. Let's just multiply this out right away. So we get a 2/3 x, and this is 3/2 minus 1. So if we put those exponents together, we're going to have x to the 1/2. And definitely that's something we can integrate. So our first term, remember, is our u times our v. So this is going to give us our first term. So put the 2/3 out in front. X to the 3/2 natural log of 4x minus the integral. The 2/3, you can put that out in front if you want to. We have x to the 1/2 dx. And take the antiderivative here. So if you have to write down a row, that means you still have to integrate it. If you don't have to write down the row, if you get a 0 here, then we don't integrate because we just get we've already integrated, we get the diagonals. So we have to take the integral here. Right answer, this is x to 3/2, natural log of 4x. And bump it up a power, so it's going to go up to x to 3/2. And we have to divide by 3/2, which is the same as multiplying by 2/3. 2/3 times 2/3, that's already there, is going to give you 4/9. And then don't forget the plus c. All right, 17, x secant squared of 5x. Integration by parts, d, I, plus, minus, all the way down. We have two things looking here. We have an x and we have this secant squared. So which one should we put in the d column? Well, again, first choice is something that's easy to differentiate. I think x is pretty easy to differentiate. But to do secant squared, you're going to have to use like the chain rule to differentiate it. Secant squared, though, is easy to integrate. If we take the derivative of x, eventually we're going to get down to 0. So again, that's a good choice to put in this column. We want x here, and we want secant of 5x here. Secant squared of 5x. Take the derivative. The derivative of x is just 1. The derivative of 1 is just 0, so we do end up with a 0 for this one. On this side, we have secant squared of 5x. The integral of that is tangent of 5x divided by 5. Then we have to integrate again. So remember, there is a formula that we had. Here's what the formula looks like. So we have a formula for tangents right here. It's natural log of the absolute value of secant. So there's the formula that we're going to use. So this is going to give us natural log of secant of 5x over 25. And we just, since we got a 0 here, we don't have to do any more integration. We did the integration to get to this step right here. So we get our answer just by multiplying along the diagonals, and once we get to the 0, we don't have any more terms. So our first term is going to be x tangent of 5x over 5. Second term is negative 1 times this guy, which is going to be negative natural log of secant of 5x over 25 plus c. 19. This one involves natural log of x plus 1. Okay, we're going to do integration by parts again. So d, I. What's going to go in the d column? Put in our signs here. Plus, minus, plus, minus, plus, minus. Okay, alternate. The d column, well, we don't really have too many choices here. It looks like there's only one thing here. Okay, and it has a natural log, so natural log typically is going to go in the d column. So we're going to differentiate natural log of x plus 1. What's going to go in the I column? Doesn't seem like there's anything left. But dx, 1 dx. So you're going to put the 1 there. This times this should give you what's inside the original integral. Take the derivative. The derivative of natural log is 1 over u. 1 over x plus 1 on this side. Times the derivative of the inside, which is just 1. So there's our derivative. We can see that, if we take the derivative multiple times, it's never going to come to 0. So let's see what we get in this column. If we integrate, we're going to have x, and this product is going to be something that we can integrate. So since we don't end up with a 0 here, we are going to have to set up a little integral here. This is our integral of v du, and we're going to have to figure out what that is. So our first term is just the product of u times v. So it's going to be x natural log of x plus 1. And then we have minus this integral. Since we didn't get a 0 here, we can't just write down the answer like we did in the previous one. And this is the integral of x over x plus 1 dx. Might seem like that's a little bit hard, but that's not too bad because we can do u substitution there. So off to the side here, we think, okay, we're going to do a u substitution. U is equal to x plus 1. Du is going to be equal to just dx. And we're going to have to do like a long division type of trick. So we have to rewrite the top here because it's not going to go away. So if u is equal to x plus 1, that means that x is equal to u minus 1. We'll write down this part. This part we need to split. So we're going to write x as u minus 1 over u. Dx is going to become du. So we do a u substitution here to change it. And now we can divide this out into the integral of u over u, which is just the integral of 1 du. And then this is going to be plus the integral of 1 over u du. And we get our final answer. So this is the first part, x natural log of x plus 1 minus the integral of 1 with respect to du, or with respect to u, is going to be x plus 1. And then we have the integral of 1 over u, which is going to be natural log of u, which is x plus 1, plus c. Now you can see you're going to get a constant here. This constant would be absorbed into that c. So for your final answer, we would have x natural log of x plus 1 minus an x. This negative 1 would get absorbed into that c. We're just going to put that at the end. Plus natural log of x plus 1 plus c. That's what the final answer looks like. All right, 21. 21 is an interesting problem because although this is on integration by parts, you could actually have solved this one by u substitution if you just let u equal natural log of 4x. And then du is going to be 1 over x, which you already have, dx. So you could use u substitution here, but we're going to do this by integration by parts. The thing about integration by parts is that it works even if you don't necessarily need to do integration by parts. If it's just a u substitution, integration by parts will still lead you to the correct answer. So we're going to do our integration by parts here, and here the parts though a little bit different because we're going to have our derivative and then our integral. Integrate d and I, and the thing that we want to differentiate is just one of those natural logs of 4x, and then the thing to integrate is going to be just the other natural log of 4x over x. And now since this is over x, this is something that you will be able to integrate. And don't forget your signs, plus, minus, and so on. The integral of this is going to be 1 over 4x times 4, which hopefully you can see is just going to be 1 over x. And this one, you're going to have to do u substitution with anyways. And so that's going to be, to integrate that, is going to be, so here you would integrate using u substitution. U is equal to natural log of 4x. Du is equal to 1 over x dx, because it's 1 over 4x times 4. And now you can integrate this. U is going to go up to u squared, so this is going to go up to natural log squared of 4x over, becomes a 2 here in the end, because you're raising it to the second power divided by 2. And now this thing looks the same almost as what we started with. So notice that what we have here is a good example of, now it doesn't come out to something that we can integrate easily, but it comes out to the original because we have natural log squared, which that's what this is, of 4x over x, and then the only thing is that this has a 1/2. So if we set this up, we have our first part, which is natural log of 4x times natural log squared, which is going to be natural log cubed of 4x over 2, or 1/2, minus 1/2 of this guy, which is natural log squared of 4x over x dx. And this, notice, is the same as what we started. Well, we're saying that this is equal to the original. All of this is equal to the original natural log squared of 4x over x dx. So this integral and this integral are basically the same, except this is a half of it. So if we add these together, we can move this to the other side. So this is going to go over here. That's going to give us 3/2 of the original integral. Is equal to natural log cubed of 4x over 2. And if I want to solve for the original integral, which is what we have up here, I just need to get rid of the 3/2. So we're going to multiply both sides by 2/3, multiply this side by 2/3. The 2's would cancel. And our original integral is equal to natural log cubed of 4x over 3. So the final answer is just going to look like this. Natural log cubed of 4x over 3. And then don't forget the plus c. So I was running out of room here, but this one's a little bit tricky because the row here, we end up with the basically kind of the same thing as what we started with, just a half version. So we have a half version of the original integral is equal to the original integral. And we can add the integrals together to get 3/2 of that integral. 3/2 of that integral is equal to this part, which is the u times v. And then multiply both sides by 2/3, multiply this side by 2/3, and we get our answer, which is going to be natural log of 4x cubed over 3 plus c. 23, we have inverse cosine of 2x. So inverse cosine, not something I know how to integrate by a formula, so we're going to have to use integration by parts. It is something, though, that we have a rule for to take the derivative. So you'll have to look up that rule for inverse cosine. We can take the derivative of inverse cosine of 2x. And what's left over for the integration part is just going to be 1. Don't forget the signs, plus, minus, so on. Look up the formula for inverse cosine. On the bottom, it's going to be the square root of 1 minus this thing, u squared, which is going to be 4x squared. And then du, it's going to be negative 2 on the top. So again, this just comes from the formula. The integral here is just going to be an x. Now you have to realize that this is going to be something that we can integrate. So our answer is going to be this times this, which is x inverse cosine of 2x. And then we're going to subtract off this integral minus the integral of negative times negative. We can make that into a positive. We got 2x on top, 1 minus 4x squared on the bottom, dx. And you might think that we can't take the integral of this thing, but we can. This is going to be a u substitution. Notice we have our u down here, and the derivative is at the top here. So if you let u equal 1 minus 4x squared, then du is going to equal negative 8x. And we already have it. We have the x part matching up here, negative 8x dx. It has a 2 there, so that means that du divided by negative 4 is going to be equal to 2x dx. So the 2x dx, this part right here, is going to be replaced with a du and a negative 4 divided by negative 4. So we have x cosine negative 1, 2x. Here the integral is going to be 1 over square root of u. So let's just write this out in u form here. So this 2x dx is going to become du over negative 4. We'll pull the negative 1/4 out here. And we're going to have u to the negative 1/2 because this is our u. We're taking the square root of it. It's on the bottom, so it's u to negative 1/2 du. And that can give us our final answer. Minus 1/4. This is going to get bumped up. 1 minus 4x squared. Raise this up by 1, so it's going to become a half. We're going to divide by half, which is the same as multiplying by 2, so actually we can put a 2 out here. So this becomes a negative 1/2 out in front instead of negative 1/4 plus c. And there we go. There's our final answer. X inverse cosine 2x minus 1/2, and then our 1 minus 4x squared, that was our u, raised to the 1/2 plus c. All right, 25. Integral of cosine of 5x times e to negative x. So this one, again, is kind of interesting. So we're going to set up our columns here, our table, d, I, and plus, minus, plus, minus. Again, the thing that we want d to be is something that's easy to differentiate. The thing that we want I to be is something to integrate. If possible, we want the d to go down to 0. But in this case, you can see that we have cosine and we have an exponential. So whether we differentiate the cosine or we differentiate the exponential, neither of them are going to go down to 0. They're both pretty easy to differentiate. They're both pretty easy to integrate. In fact, in this one, you could choose to put the cosine under d, or you could put the e to the negative x under the d. So this one can be set up two different ways. You can put the cosine here and the e to negative x here, or you can put the e to negative x here and the cosine over here. And you're going to find out that, you can solve it either way, I believe. So for me, I'm going to put e to negative x here and cosine of 5x over in this column. And we're going to take the derivative. The derivative of e to the u is e to the u times du, which is negative out in front, and take the derivative again. We're going to have e to negative x, and then times the derivative again is going to be positive. And we can see it's just going to kind of flip-flop between those two. If we do this integral for cosine, that's going to be sine of 5x divided by du, which is going to be divided by 5. If we take the integral again, it's going to be negative cosine of 5x divided by 25. Now the thing to watch out for here is, notice we started out with a cosine of 5x, e to negative x. And here we have e to negative x, cosine of 5x. The constant here doesn't matter too much. We basically have what the original was, just with a constant multiplier. So we're going to stop at this point and write out what we have. So this one's a little bit tricky. So we have, let's just write out what our original integral was. Here's our original integral, and I'm going to put the e to negative x out in front. And we have cosine of 5x dx. And we're saying that that integral is equal to this product, u times v, which is e to the negative x sine of 5x over 5. And then we have this integral. A negative times negative makes it positive, but when we got another negative, so it's negative e to negative x cosine of 5x over 25. Then we have this integral, and it's a positive times a negative, so it's going to come out to negative. And the 25, let's put that out in front actually. So 1 over 25 out in front, and we have e to negative x cosine of 5x dx. Notice that this and this are the same. So these two integrals are exactly the same. So we can put them over together. Here we have one of them. And if we're going to add 1 over 25, that's going to give us 26 over 25 of the original integral equals, and what do we have here? E to the negative x sine of 5x over 5 minus e to the negative x cosine of 5x over 25. And we still don't have the original integral by itself, so we want to solve for the original, which means we have to get rid of this constant, which means we have to multiply everything by 25 over 26. So 25 over 26, multiply this by 25 over 26, and multiply this by 25 over 26. The 25 and the 5 here would cancel, and I have 5. Here the 25 and the 25 would cancel. So the final answer is going to look something like 5 e to negative x sine of 5x over 26. And these are both going to be over 26, so I can just put this guy in there too, minus e to negative x cosine of 5x plus c at the end. I can squeeze that in. So again, because you can't read it, it says 5 e to negative x sine of 5x minus e to negative x cosine of 5x all over 26 plus c. 27. So this one has the e to the 3x on the bottom. It's x squared. To start out, maybe we should rewrite this x squared e to the negative 3x dx. Set up our columns, d and I, plus, minus. So here we have a polynomial and we have an exponential. If we differentiate the exponential, it's not going to disappear. If we integrate it, it's not going to disappear. However, if we differentiate the x squared, that will eventually disappear. So we have x squared, 2x, 2, 0, just taking the derivative until it gets to 0. If we take the I, then is going to be e to negative 3x and we're going to integrate that. So that's going to be e to negative 3x over du, which is going to be negative 3. And then integrate again, e to negative 3x over, divided again by negative 3. So now it's 9. And e to negative 3x divided again. Now it's over negative 27. And now we get a 0 here. So we can just get our answer by multiplying down the columns. This is going to be our first term, which is going to be x squared. And it's a positive, but this is a negative, so we're going to take the negative out in front. X squared e to negative 3x over 3 minus, here we got a negative times a positive, so it's going to be negative. The 2 is going to be on top, 2x e to negative 3x over 9. Of course, we could put these negative 3, we could write it as e to the 3x on the bottom as well. And then the last term is a positive times a negative, so it's going to be negative 2e to negative 3x over 27 plus c. And there's our answer. 29, x squared sine of 5x dx. So set up our columns, d, I, plus, minus, minus. And again, similar to 25, similar to the one above, where we have an x squared, and then this sine of 5x, we can differentiate and integrate both of them pretty easily. But if we differentiate the sine, it's just going to flip between sine and cosine. But if we differentiate x squared, eventually it goes down to 0. So that's good. That means it's going to stop. If we take the integral then of sine of 5x, that's going to give us negative cosine of 5x over 5. Integrate again, it's going to be negative sine of 5x over 25. Integrate again, it's going to be cosine of 5x over 125. And then we get to 0, so we don't have to go any further. So we've got our answer. Just multiply along the diagonals, and we've got these three terms. So the first term, positive times the negative, is going to be negative x squared cosine 5x over 5. Second term, a negative times a negative makes it a positive. 2x sine of 5x over 25. Positive times a positive. 2 cosine 5x over 125 plus c. So we've got our final answer. Again, this involves an exponential and it involves a trig. And again, I don't think it matters in this case when you have an exponential and you have a trig, which one is your d and which one is your I. Maybe I'll do this two different ways. So we can have d being the exponential, e to the 4x, and I being the trig, the cosine of 4x. Plus, minus. When we differentiate it, it's going to be e to the u, du, where du is 4. Differentiate again, it's e to the 4x times 16. You can see that it's never going to end, so eventually it should start to repeat. So let's look at what the integration does. Take the integral of cosine, it's going to be sine of 4x over 4. Integrate again, it's going to be negative cosine of 4x over 16. And you can see when you multiply these, we basically have a form of the original. It's just going to be a minus sign here, which is fine. So our original integral of e to the 4x, cosine of 4x, is equal to u times v, which is e to the 4x sine of 4x over 4. Here's the next term, a negative times a negative makes it a positive. 4 over 16, that's going to reduce down to 1/4. And we have e to the 4x cosine of 4x over 4. And then we have this integral at the end. The 16s would cancel out, so we have minus the integral of e to the 4x cosine of 4x dx. But this is the same as the original, so we can add them together. Here's 1 plus 1. That's going to give us 2 of the original integrals. And I'll just write it out. 4x dx, forget the dx there, is equal to e to the 4x sine of 4x over 4 plus e to the 4x cosine of 4x over 4. But then we're going to divide both sides by 2. So just change those to an 8 and add c to it. And we've got our answer.